To part C of our lab number 1 for business applications for machine learning. Today, in this slide, we actually want to start talking about the math behind building our trees. In this case, classification regression trees. CART. The algorithm is called CART officially. It's called something different in R. But the classification regression trees, this is basically a way to, again, build classification models, classifier models, if you will. But it's also a way to do predictions, all right? Where more of your classifiers or algorithms that are utilized in machine learning, they come from the world of probability and statistics, right? For example, regression, naive Bayes, etc. This methodology is more similar to how we as human beings make decisions, right? Which is why I love it, right? Statistics doesn't tend to work in my space, the financial investment space, because of nonlinearity and all these other issues. So I really love decision trees, and classification regression trees, and that's why it's kind of very popular in the machine learning world. These type of models. One, there's a cool factor. Two, it's just more intuitive for a lot of quants, right? When we make decisions, our brain, we tend to, like, for example, here we have an example of where we want to identify an animal, right? A particular animal. If you look at the picture on the left. And what we want to do is, when we identify an animal, we basically look at the features of the animals in our brain, and then based on these features, we make a distinction. Okay, this is this animal, this is that animal, right? That is essentially how classification regression trees work. It it takes a list of features and then attempts to quantify those features in such a way that it can predict what in this case, a certain animal, right? It predicts a certain animal. And the way it does this is by, obviously, you have to give a set of data to the classifier, and it's going to train the model, and we'll talk about this. And then once you have a model defined, you can use it to attempt to do other predictions on your data, right? On your data. Now, again, given the group of animals we have in the beginning, right? We have giraffes, elephants, cheetahs, a monkey, right? Our mind differentiates based on, again, different features of the animals, right? Using those features, we predict, again, or classify what the animal is, right? The example is the color yellow, right? If you look at the rules here in this particular tree, the first rule is what the color equals yellow, and then they went to the height. And based on just these two features, we are able to differentiate the giraffe from the elephant, the cheetah, etc., etc. Mathematically, that's how these trees work as well. They take certain features you give it, and then they try to build rules around it so that they can predict or identify, in this case, what each certain animal is. Now, this particular algorithm was made, I think, Leo Bremen and his colleagues in the 1970s, and it's called CART. The implementation version of this in R is called RPART, okay, recursive partitioning in regression trees. The only reason behind this is actually funny is because CART was trademarked by Bremen and his crew. So this is why they called it RPART. And R, right, it's essentially the attempted to apply the mathematical algorithms that this guy and his team created in trying to do this kind of analysis with data. Ironically, now the algorithm tends to be called RPART more often than it does CART. So that's a fun fact. All right, now this data right here, this example, this is the data behind it, right? This is the data behind it. RPART, essentially, it creates what we call splitting rules based on the independent variable, so that you can create groups that are pure, groups that have less amount of variability, groups that are homogeneous, right? Groups that are homogeneous. So we're always attempting to try to reduce the amount of Geneity, geneity, geneity. Sorry, I keep mispronouncing it. Heterogeneity. The heterogeneity in each one of these groups, right? In other words, we want to make it the same as possible. So we want a separate group for giraffes, separate group for cheetahs, separate group for elephants, separate group for monkeys. Essentially, what our part does, it takes this table, right, and it's attempts to break this table down into, at least that column, animal, because animal is our dependent. That's our dependent variable. Color and height are are independent variables. Same thing like regression, if you want to think about like regression. We're using the same lingo, if you will. We're using color and height, right? We're using color and height to attempt to predict the animal, right? But how are we doing this? The way our part essentially works is it tries to take that animal column and break it into subgroups that are pure. So you have one group that has the giraffes, one group has a cheetah, one group has the elephant, and one group has the monkeys. The way it attempts to break up that table, that column, into those subgroups is by applying rules to your independent columns, the color and the height, right? The color and the height ones. So that you can create some sort of rule about what the color should be or what the height should be. And then that animal column gets broken up based on those rules into a group that is more pure or that has less impurities. Here is, again, the same example. We started off with our first group, and then we broke it up into the color equals yellow. Is the color equal yellow? From color equals yellow, what happened was we broke it down into 6 animals in one group, 6 animals in the other group. All right? 6 animals in one group, 6 animals in the other group. Now look, we didn't get pure. We didn't get a full purity. Like that rule didn't break down the animal group into its 4 sets of giraffe, cheetah, elephant, and monkey, right? But what we did get is we got less variation in each group. The subsequent group that was created, the one with the giraffes and cheetahs and the one with the elephant and monkeys, it still went from having 4 unique animals in it to at least having 2 each. So that's a win, right? It got less. There's less impurity now, less impurity. Right? And from there, those subtables are then further broken down into other subtables. This happens in our part over and over again until a certain predetermined criteria is reached, and we'll talk about that mathematically in another lecture about what that means from a it's essentially a cost function. How our part creates a cost function. And then how it optimizes for it to try to come with a predetermined rule of, listen, how many times, basically. That's basically what our part does. Using the data, it comes up with and some sort of algorithm. It comes up with a predetermined list of how many times it's going to go about doing these splits. Now, look, if he gets full purity, like in this example, in the third step, we get full purity, we're done, restocked, right? But obviously, with real data sets, it doesn't work that way. With real data, you never ever technically get full purity. So our part in these algorithms need a cutoff. They need to stop at a certain point, and we'll talk about how it goes about doing that. Right? So these subtables are further split, and you can see that in those subtables, we now utilize the height column and create a rule. Hey, is the height greater than 10 feet, I guess? If it's true, then it all became giraffes. If it's false, then it became cheetahs. Same thing with the other group. If the height was less than, but this time they use height, but this time they use a different scale. They use the same column, but they use a different kind of comparison. Here, if height is less than 10 feet, right, less than 10 feet, then you became a monkey. If it was false, you became the elephant. And in just those 2 rules, color equals yellow, or I would say 3 rules, color equal yellow, height greater than equal to 10, or height less than 10, we got full purity. We created groups that have full purity, right? Giraffes, cheetahs, monkeys, elephants. This is the ideal situation. Now, what does this have to do with analysis of any kind, right? This is great. You gave this data. It broke our part broke up this data into pure sets using these rules and identified those rules. What does this mean in terms of analysis? What this means is that collectively these rules that were generated, they essentially became our classifier model or our prediction model. Now, anytime we give this data of these color and height, color of height, right? We give this data of color and height to this model. This model will take the color and height, run it through its rules, and then predict what animal we are identifying via the color and height. This is how prediction is done using trees. This is how prediction is done using trees, right? And if you have already taken BAP, you saw us use towards the end of the semester random forest classifier, right? Which is basically this concept of trees done multiple times. Forests basically are many trees. So that's what forest is. Random forest classifier was basically a simulation where it did many trees, created many of these trees, so that you have like a probability going of what's the probability that this is a different animal. But here we'll just focus on one tree for now. We'll get there. But this is the whole point of what these rules are. These rules collectively now, right? See, these rules, again, think about your mind, the way it works. So in the subconscious level, you have these rules in your brain when you're identifying something. You have these rules in your brain. Here now, mathematically, we're explicitly creating these rules given the data set. And now that we have these rules, we can pass along any combination of color and height to this model, and this model will spit out a prediction of what kind of animal it thinks it is, right? In this case, it was trained on giraffe, cheetah, elephant, and monkey. So now this model is basically, ideally, trained to predict, hey, this is a giraffe, this is a cheetah, this is an elephant, this is a monkey. That's the point. That's how prediction is done. Now, for our data set, we went through all this trouble of creating this movie data set. What do we plan to do? Well, we plan to predict a successful movie by whatever we measure success to be, monetary in our example, or a certain monetary range, if you will, a certain percentage profit range, right? So we want to identify a certain profit range to be successful. And ideally, all we want to do is we want to be able to predict, given the different factors that behind the movie, will this movie be successful or not? And this is why we're using classifier and regression trees. Classifier and regression trees are going to explicitly create these rules around our movie data set that we give it to create a model that will allow us, it will help identify for us what a successful movie will be or not. And again, that term success, we're going to quantify it based on the profit the movie made. This is why we went through all that trouble of scraping for, what the cost of the movie was, the budget, and then how much it made both domestically and internationally, right? That was a critical factor. That was a critical data set we needed in attempting to identify what a successful movie is or isn't. And again, we could play with that terminology, right? And once we do that, we can run our data set through these classification models, and we can generate this set of rules, right, that will help identify, at least based on our data set, what a successful movie will be or not. I mean, what predict basically what will be a successful movie or not. And what ends up happening is when you run this analysis, the rules that are generated, it actually gives you very unique insights into, at least in that data set that you used, how the quote-unquote successful movies, how their factors or their features were different than the other features of movies that didn't do as well. And is there a clear general pattern? Is there something that's obvious or something that's not obvious that comes about when those rules are being generated, right? It's very wild and very cool. But anyway, this is the whole point. These rules are generated, and these rules essentially become your model. Now, impurity. Now, to the heart of this is the concept of impurity, right? Measuring the heterogeneity of each one of these data sets, right? Remember, we want less heterogeneity. We want everything as homogeneous as possible. We want to reduce our impurity as much as possible in the subtables or leaf nodes, and as soon as possible. The splitting rules are basically constructed essentially using three different calculations of impurity, right? Three different calculations of impurity. I mean, there's three predominant ones, pretty much. An impurity of 0 means that the leaf node is perfect. Perfect. So, for example, down here, which are giraffes, in our third level, where giraffes, the cheetahs, these four sets, each one of these sets, each one of these subtables would have an impurity score of 0 because they're perfectly homogeneous. They're perfect. It's the same animal in each class, right? Now we enter a little bit of our mathematics behind it. We start. What are the impurity quantification methods? Like I said before, there's three predominant methods. Entropy, i.e. it's called entropy or information gain. Gini index, right, which is the default the default algorithm for R part. We can use either entropy or Gini index. They're both in R part. And classification error, which I will not discuss because classification error is not in R part. We don't have that option in R part. But we do have entropy and Gini index. Here is the fancy little formulas for both entropy and Gini index. All right? It looks more complicated than it is. But once we do like a few examples, we'll do one example here, and then obviously I'll give you a few examples in the practice set. You'll see it'll become a little more common. It'll become more intuitive. It'll become more intuitive how it works, how it calculates everything. Let's look at this example right here. All right. This is our original data set. This is our original data set of animals, the giraffes, the elephants, and cheetahs, etc., etc., etc. We want to calculate basically our initial entropy or Gini index score for our initial data set. Let's implement it. Let's start with entropy. In entropy, I have a negative here, and then I have a summation, j equals 1 to c. J equals 1 to c is basically, j is basically our iterator. C is basically stands for how many different unique classes we have in our data set. For example, C basically stands for the number of animals, unique animals we have. P of j is the proportion of each particular animal, and log base 2 is just log base 2 pretty much, right? And you'll notice that there's always a negative before it. So again, like I said before, this little symbol here basically means it's a sum across all these different unique classes. So you're going to have this equation be implemented, this part at least with the negative, be implemented for every different set of animal classes you have, or in this case for every set of animals you have. We have four unique, no, how many unique animals we have? Giraffes, elephants, cheetahs, yes, 4 unique animals. Therefore, we will have 4 of these equations with a negative. 4 of these. Remember, C stands for the amount of unique classes. If there's 4, then there's going to be 4 of them, and here you see them. Here's 1, here's 2, here's 3, and here is 4, right? Right, from here, what is the negative is obvious. Sorry. Excellent. I have my R right here. Let me pop it open. We'll do the math in here as well. All right. So the negative is obvious, right? That's part of the equation over here. What's P of j? Again, P of j, the P stands for proportion for that particular. J is basically identifying each unique class. So because we have 4 classes, j is going to take on the value from 1 to 4. 1, 2, 3, 4. All right. The first class, and it's up to you which class you want to take first, right? I think in my example, I ended up taking cheetah as first. I mean, the giraffe. The giraffe is first, all right? So firstly, if we want to know, we're calculating P of j, the proportion of giraffes. My first thing I have to know is, well, how many giraffes do I have? Okay, in my original data set, I have 1, 2, 3. 3 giraffes, excellent. Now, out of the 3 giraffes I have, that's 3 giraffes out of how many total animals in my data set or my initial table? That would be 1, 2, 3, 4, 5, 6, 7, 8. Or if we would come here, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, here it's saying 12, right? Here it's saying 12, but I'm going to go by what the image shows. All right, guys, I'm going by this image. So I know in your table, the table here it says 12. I'm doing the math according to this image. We can go And we can actually redo the whole math according to that table, but I'm doing it according to this image for now. All right, so here I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 total animals, 3 of which are giraffes. That's your proportion for giraffes, 3 of 8. Log 2 is simply log 2, right? And then in the parentheses of log 2, PJ goes again. All right, again, very simple. Negative 3/8, log 2, 3/8. That's giraffes. Let's do the next animal. I think the next animal we'll do is cheetah. How many cheetahs do you see? 2. All right, there's a negative. There's 2 cheetahs. Again, out of total 8 animals. So for our initial equation, the denominator will all be the same. It's all out of 8 animals. Okay, it's all out of 8 animals. So the numerator, again, 2 cheetahs, boom. In the parentheses, 2 cheetahs, done. Negative, next one. Let's do elephants. Okay, again, there's 2 elephants. So it's going to look just like the cheetahs one. 2 of 8, 2 of 8. Again, last one, negative, the monkey, just 1 monkey. 1 of 8, log 2, 1 of 8. You do this whole math right here, and I'll do it for you in R, and you get a score 1.905639. What does this number mean? Well, it's not 0, right? So it's not pure. That's all it means at this point. What does it do for us? What does it do for the algorithm? It doesn't do much until we attempt to start splitting it. Okay? The idea here is we have this starting number, 1.9056. We want to get to that to 0. So we want to choose a rule. We want to choose a rule that will give us the biggest reduction from 1.90 to the next lowest number. That's pretty much it. Which rule will give us the biggest reduction from 1.90 towards 0? Towards 0. That's the idea. What rules are going to get me to 0 the fastest? Those are the rules we want. That is the game happening behind the scenes of the algorithm. Right, now let's do this for Gini. The Gini index, being more simple, is simply 1 minus, again, j equals 1. Basically, j equals 1, summating over till c. C is basically the unique number of classes you have, again, or in our example, the number of animal groups we have, which are 4. So we're going to have 4 equations, little mini equations. And here, P of j, the ratio, we're just squaring it. So this is actually very simple. So here we just do 1 minus the ratio of giraffes, 3 of 8, squared, minus ratio of elephants, 2 over 8, squared, minus ratio of cheetahs, 2 over 8 squared, minus the number of monkey ratio, 1 over 8 squared. And again, we get this number, 0.71875, which again is not 0. Is not 0, right? But it's our starting point. What rule will get me to 0 the fastest? All right. In other words, what rule will drop that 0.71 down the furthest? What rule will reduce these numbers the most? That is what it all comes down to. Let's go ahead and do this math. In here. All right. Times. I could just wrap it in parentheses, keep it simple. Log. Notice I put log. There's my log base 2. So simple. 3/8. All right. And I'll just copy this for the other ones. Boom. Change this to, for the elephant, for the cheetah, don't even have to change that many numbers. And now for the monkey. Bam. And you see my number I get is 1.905639. Very straightforward. Right? My starting point, guys. Let me go ahead and do it for using the Gini index. 1 minus, which is even simpler. Steal that right there. To the power. Remember, we want to square it. And I'll just do it for everything else. This becomes 1. Bam. 0.71875. See that? Very straightforward, guys. Very straightforward. From here, let's look at it. Now the rules were already predefined, right? Color equals yellow. Color equals yellow was our rule. Color equals yellow was our rule. So what happened? All right, what happened? When color equaled yellow, what happened to entropy? Right? What happened to the entropy and what happened to the Gini index? In this case, we're going to do it. We broke we had two different groups subgroups were created. So we'll calculate both entropy and Gini for both subgroups, right? So in this case, what happened was, all right, yeah, here they're showing again only, I think got it cut off. One of the giraffes got cut off. But again, our initial 8 animals got broken up into 3, a group of 5 and a group of 3. All right. Color equals yellow, so that means the 2 cheetahs and 3 giraffes went in this group. And then color equals yellow is false. The 2 elephants and the 3 monkeys went in this group. All right. So what ends up happening here is, what is my new entropy score? Again, I'll start with giraffes first. There's 3 giraffes, but now the denominator turns to 5. Why? Because this group now has 5 animals. This group now has 3 animals. So across the board, now there's 5 animals, right? And it's only going to be 2 equations now because I only have giraffes and cheetahs in here. So there are 3 giraffes out of 5 animals, 3 out of 5, minus 2 cheetahs out of 5 animals, log base 2, 2 over fifths. And this is my new entropy for this group. I do the same thing with Gini. 1 minus 3 giraffes out of the 5 animals, squared, minus 2 cheetahs over 5 animals. Square that bad boy, I get 0.48. All right, now look at the difference. Originally, my entropy score was 1.90. It fell in this group from 1.90 to 0.97. All right. Over here, Gini was 0.718. It fell to 0.48. So we got a big drop toward 0. Let's look at the second group. Right, the second group. 3 animals. 2 elephants out of 3 animals. 2 elephants out of 3 animals. Minus 1 monkey, basically, out of 3 animals. 1 monkey out of 3 animals. Entropy becomes 0.91. It becomes even less than the other one, right? 1.9 becomes even less than this one. Gini index, same thing. 1 minus 2/3, 2 elephants out of 3 animals, 1 monkey out of 3 animals, and this becomes 0.44. Right? Again, big drops. That's what it's all about. This is why this rule was picked first, because this rule gave us the biggest drops. In this case, even though we're doing both calculations, the default here is really Gini index. Gini index is really the default, but we couldn't use either or. The follow-up question will be, well, why would you use entropy over Gini or Gini over entropy? We can talk about that a little bit later. There's different debates and topics about this, and we can discuss that. We can at least approach the different issues or points that certain people make over one versus the other when you're using this kind of using these impurity model equations, these impurity calculations. All right, from here, guys, we saw if we took the weighted average, right? We took a 5/8 from here, minus 3/8 from here. Remember, because the 5/8 was from this part, and we're basically taking a weighted average. So 5/8 of our data got a score of this. 3/8 of our data got a score of this. 5/8 of our data got a score of that. 3/8 of our data got a score of that. And we basically, right, if we subtract the original one, we see that our reduction in impurity was by 0.95. Right? It was like weighted, if you will. Our reduction was 0.95. Right? We went from, this is the reduction in impurity we actually gained. In this example, typo here. In this example, when we're using Gini index, this is the amount of reduction in impurity we gained. And that is basically it. We want to gain as much reduction, and it's kind of wordy here, but we want to, or basically we want the most reduction in impurity. Get the rule that gives us the most reduction in impurity. How does these algorithms, how does the R part even calculate this? Again, we'll explore that a little bit later, right? Some of these complex algorithms, how they break it down, but that's essentially what's happening behind the scenes. right? And this finally gets us to this part where we talk about, and here at this point, we'll end with this slide, but essentially at this point now, we want to talk about what it is that we're trying to do in terms of decision trees, right? And this is going to be new for you if you've never done classifier models of machine learning. When you get this data set, right? If we have this data set right here, here's an example. We take this data and we feed it into our part. Our part creates these rules, creates this nice little graph, bam, and we have a decision model basically. We have a model that allows us to predict certain animals, right? Well, that initial data set we gave, that was what we call the training data. The training data. That is the data that basically creates our model. That creates our model. We have another set of data. We have another set of data that's called the testing data. And that data, what that testing data is, when we train our model, we then run our testing data over that model. Now, why do we do this? We do this because we want to see how accurate our model was. And that is why when we have a data set, we break it up. Usually the rule is 2/3 are the training data and 1/3 is the testing data. Because you want to basically see when you provide just the predictors, right? For our testing data, just like our training data, we have the predictors and the target. Again, our independent columns, here this particular example is basically given the certain weather, should you play golf? Yes or no, right? Or it's predicting whether an individual or a group of individuals, whether they'll play golf depending on a certain weather pattern, okay? Now, this data set comes with both the independent columns and the dependent columns, or the predictors and the targets, okay? The predictor columns and the target columns. We break up this table into its training data and its testing data. Again, like I said before, the general rule tends to be 2/3 of the data rows are used towards training data, randomly we select it for training data, and 1/3 we randomly select for testing data. All right. We use the training data and we build this model. Again, here's a hypothetical decision tree that is built, right? Hypothetical decision tree that is built. All right. Now, given that this tree is built, this model, if you will, we then take our testing data. We just take the predictors now of our testing data, just the predictors, and we run our data through this model. We run our data through this model, and we run it through our model to see what gets predicted. In this example, given the data that we run through this model using the rules, what does it predict? Does it predict we play golf or we don't play golf? And we get all these predictions. And then what we do with these predictions is we compare these predictions to our actual target value associated with the testing data. You see, we have what the right answer was according to our testing data. That's why it's called the test data, because we predict what the results will be, and then we compare our prediction to what the actual results were associated with that testing data. Right? And this allows us to build, I don't have the slide here, I'll have the slide in the next set. You guys have probably done this a lot in other classes, but this allows you to do basically it allows you to test for accuracy, false positives, true positives, etc., etc. Basically, what we call our classification table, right? And you guys will see this, and the different, I would say, analytics you generate off these tables, right? When you have your actual values and prediction values. All right, and that is why you will hear this concept over and over again. The concept of training data and testing data. Training data and testing data. And again, I'm sorry, it's confusion matrix. That's the term that was alluding to me. Confusion matrix. When you take your predicted data and compare it with your actual data, you can create what we call a confusion matrix that allows you to measure your model for accuracy, how accurate it was, how the true, like I said before, the true positive rate, the false positive rate, the precision, the misclassification, right? Or error rate, as it's known, right? So these values help us identify, hey, how good was that decision tree anyway, right? Because remember, the computer, the R part is generating this decision tree. But the question is, how accurate was that decision tree in doing predictions? Well, that's where the testing data comes in. That's where the testing data comes in, right? And if technically, I mean, to keep it simple, if the testing data, when we run the testing data through our calculated, generated decision tree, and the accuracies are fantastic, and the misclassifications are low, and the precisions are high, and the recalls are high, right? Then that is something that tends to be a good model we generated, right? And again, the data generated that model. The data generated that model. It created a program, if you will. If you come here, back here, right, into here, I can write a program. I can write a program that will identify the model. I will write a program that says, hey, if the color equals yellow, and I'll do an if-else statement. If the color equals yellow and the height is greater than 12, then you have a giraffe. Or, I'm sorry, greater than 10 or something, you have a giraffe. If the color equals yellow and your height is less than 10, oh, then you have a cheetah, right? Or something along those lines, et cetera, right? I can code this. The problem is, once I code this, right? Firstly, once I code this, I have to keep recoding it as I get new data. In the world of machine learning and classifier models, the data keeps changing. The model keeps changing, right? Think of along the lines of spam. Spamming is a great example to give over and over again. Spamming, the spamming is basically a machine learning algorithm that basically keeps seeing what you identify as spam. As it gets more and more data for what you identify as spam, it basically takes those features, runs those features through this prediction model, a decision tree like this, and generates rules. Those rules are dynamically generated by the data you keep giving it, and those rules keep getting refined so that it keeps predicting what is spam and what is not. And sometimes, look, your spam algorithm sometimes make something spam that shouldn't be. I mean, sometimes you go in your spam folder, or somebody tells you go in your spam folder, and you say, make this not spam. The algorithm gets that. Right? The algorithm's like, all right, cool. Here, in this sense, I got it wrong. That's your test data right there. And then again, it refines the model more and more. Imagine if you had to keep programming this. You have to go in and put more if-else's, make more nuances, right? Like in this example, I could do a simple code, but as I get more animals or more data, I have to go in and keep changing the code. Whereas the data, right, that here you have more like a feedback loop going, where as you get more and more data, you feed that data into your decision tree prediction model, right, or classifier tree model, and then you can see the predictions, and you can keep going back to say, hey, this prediction was solid, this wasn't, this wasn't. This is what data scientists do. They get these predictions, they use predictions, and then they go back and say, okay, this prediction was right, this wasn't wrong. And they keep telling the algorithm this was right, this was wrong. It's basically giving more and more test data, if you will, training data and test data. And it's getting more and more data, and it keeps refining the rules. The splitting rules, basically. Your splitting rule. It keeps refining it. What is happening? What is it doing? It's creating its own program. What it's essentially doing is programming. It's programming these decisions. It's generating its own programmings via the data. Or it's learning. Your program is learning and adapting and changing. This is why we call it machine learning, because more data that is now tagged or labeled, if you will. Basically, basically what I mean is, when a prediction was done, we go back as data scientists and say, okay, this prediction was right, this prediction was wrong. Here you go. here was your predictions. This one's was you right. This one's were wrong, and it goes back into the training data. And the training data keeps getting updated and refined, keeps getting updated and refined. Subsequently, that keeps updating and refining our classifier model, or the machine keeps learning and learning and learning. This is why we call it machine learning, guys. This is why we call machine learning. And again, there's several different algorithms out there. There's various different algorithms out there for machine learning. I started it with the classifying and regression tree part, or our part in ours, because this is probably among the most popular, or one of the more popular algorithms used in practice, in application in the industry. So I definitely wanted to cover this, and this is what we're going to use to basically create our prediction model with our movie data set. All right, guys. So we'll end the video here, and I will give you a couple practice set problems with doing the math, basically doing the math between the entropy and reduction. Yeah, giving you the math between reduction and impurity. I'm thinking, even though I didn't go over confusion matrix right now, I'll probably do some confusion matrix thing too, or I'll leave it for next slides. But I'll definitely give you some entropy and some math equations right now, just so you guys can get comfortable with the impurity index and how it works. All right, so this ends this video, guys, and I will see you guys at the next video or the next class. All right, have a good day, and bye-bye.